Okay, let's start. As usual, right, I would like to nag on the same things. Okay, so we finished lessons, right? You should still go back and review the concepts which are covered. For past few weeks, right, we have done at least 3 or 4, is it 3 or 4? Around there, paper ones. Paper ones are very good for another fresh round of revision. Why? Because, right, each time you do, you cover 20, 30 modules of concept. Okay, so you can comb through a lot of things and revise them really quickly. But right, you must make sure that you learn the thing properly. Okay, so don't just stop at the answer. Always right, go through, follow through until you totally understand explanation. So if today you go back, okay, some of the things you don't catch, watch again. Okay, the video. That's why I try to post as fast as I can. Usually, right, if I don't have coaching if I have coaching, I'll post it in the evening. Once I get home, right, immediately, before I even eat dinner, I tell you my routine. I reach home, right, immediately set up my laptop, download the recording, right, then I need to process, to remove the silence. So that process 10.5 hours or 2 hours, depending on how long is the lesson. And after that, quickly, right, upload to YouTube, wait for it to process, because that whole thing takes a few hours on. Yeah. Let's start. Okay. Today, right, later on, if you need to go early, you just excuse yourself, okay? Because you have the recording. If you can stay, just stay and learn on the spot. First question I think is straightforward. Most people, so what we are looking for, right, is the line of action all intersecting along one point. Okay, therefore, right, the answer must be C. Okay, so why must this be so? Because we covered this during the static equilibrium division, I think. Okay, well, for net moment to be zero, right, for three forces, if they don't intersect at one point, you can just argue by the contradiction. Then you take moment about the intersection of any two other forces, then there will be a net moment. Okay? So only when they all intersect at one point, right, then they will result in no net moment. So this is something that you need to know, okay, for three force situation. More forces, right, may not be true already. Unless more forces, you can reduce it back to a three force. Next up, so this question, right, multiple way of solving. Show you the more traditional way, then we talk about the shortcut. Traditional way is to look at force by force. So you see, you have a 4G here and a tension here, which is unknown. You have a tension here and a 2G here. Okay, so this guy is accelerating up, this guy is accelerating down. So you can write net force equals to MA. So let's call this method 1. So 4G minus T equals to 4A. Then T minus 2G equals to 2A. Okay. If you don't know any other way, right, this way is very safe one. Confirm get the answer. Or 1 plus 2. 2G equals to 6A. Okay. So A equals to G upon 3. This is one way of getting the A. The second way of getting the A, right, is to simply look at the unbalanced force. Okay. So what is causing the whole system to accelerate, right, is because, did I draw the arrow wrongly? I believe I did. What is causing the system to accelerate is because one side heavier than the other side, right? What is the imbalance? The imbalance, right, is the 2G. So you can straight away, right, apply net force equals to MA to whole system. Okay, so to whole system, right, what is this net force? Is 2G. What is the M that the whole system have? Is 6. Therefore, right, you see, you get the exact same outcome as treating them as one body by one body. So once you know the A, right, then you can figure out that when they are the same height, each of them must have moved by 5 cm. Okay, so you use the V square equals to U square plus. Reminder, convention is very important. Okay, you can apply to anyone. Let's apply to the 4. Okay, so you have V square equals to 0 plus 9.81 upon 3 and 0.05, and you get answer A. One last way, this is right using COE. So you can use right consider who is losing energy. It's right loss of GPE of the 4 kg, and this is equals to gain in GPE of 2 kg, gain in KE. So I leave you to do all the working. You get the exact same equation. This yet another way. This question, right, may look easy, right? And indeed it is. And nowadays, right, actually I feel if you find that you are not doing so well yet, right, these are the kind of questions that you need to be very familiar with, very proficient. Why? Because this is the bread and butter. They form out the bulk of the MCQ paper in A level. This is the level of difficulty that you are really hoping to be very proficient. All these kind of questions must all get right, so that you can leave buffer for losing marks in the difficult questions. I'm going to do some questions because the hard copy, right, arranged slightly different. So this one is on the last page of your hard copy. Yeah, because when I do this version, right, I bring it forward already. This hard copy or soft copy that you have, right, you're looking at is because certain questions people sending me much later, and certain questions, right, if I put them in the numerical order, I may use up too many pages. So I combine shorter questions to occupy same page or same paper. Anyway, for this one, right, how to do? This one is, I think it's not too difficult. Consider the potential, right, as being the formula for potential is Q over R, right? Okay, so you see this is a plus, this is a minus. The potential at X, right, just due to these two charges alone, right, will sort of cancel out. They plus together to give you 0. Same for the other two charges, because they are equidistant from X. So at X, right, what's the potential? Potential is, what's the potential at Y? Still 0. Because, right, the same thing can be said for the effects of the positive charge and negative charge, right, sort of cancelling out each other. Yeah. So is there any change in potential energy? And therefore, right, is there any work done by external force? This is similar, right, to, let's say if you have a dumbbell or 10 kg dumbbell in your arm, or you hold it in your muscle, you feel, wow, feeling, right? But if you move it horizontal, okay, hold the dumbbell with your arm bent, right, hold and move it horizontal, there's no work done. Or muscle strain is your muscle strain. It's a different problem, okay? But there's no work done. It's the same because you're moving it along the same potential. And that is the same, right, at all points. It's not just at this point. Because this point, right, X and Y happens to be at a bisector. And these two charges, right, these two sets of charges are same quantity, opposite poles. Therefore, right, the relationship will have O anywhere along this line. Okay, you can flip back to the original part of the paper. Okay, next question is quite difficult to get right. Did I miss out some question? For this one, right, it's actually quite tedious somewhat, okay, when you really try to do it. First part, right, is to understand what is the effect of the accelerating potential on the velocity. Then, right, you will link the velocity to the radius of curvature, like 4 sides, right? In the end, when you see this radius of curvature, right, you know that in the formula, there's a mv over bq. So you see, what you want is the q over m. Yeah, it appears inside this formula. Therefore, right, but this formula also have the v. Okay, this velocity v, right, don't appear in any of the options. So you need to relate the velocity v to accelerating potential. So step 1, right, is to look at the acceleration part. If the loss in the EPE equals to the gain in the KE. Okay, charge is charge Q times the capital V. This is equals to half mv squared. Okay, V square will be equals to Q capital V. So V equals to 2 capital V Q over M. Okay, so this is like the equation 1. The equation 2, of course, is the radius of curvature. So R equals to mv over bq. So you can sub in already. Yeah, so you see you'll get a messy formula. The m, right, and the m inside the square root, right, will sort of remove the square root. Okay, I mean, so you will have left with a m inside. On the outside, right, you have a inside the square root for v, right, you have a q over m. Okay, so here you will have a, wait a minute, that's not what I want to do, sorry. Let me erase y equals to mv over bq. Let's make the q over m the subject first. So, right, this all turns into q over m equals to over br. Okay, I hope I never get this wrong. Okay, then you sub in the v. So you have m over br, you have 2 capital V q over m. You see, q over m now appear on both sides of the equation, right? So I want to divide by square root q over m throughout. So this gives us, right, square root q over m. The right side no more already. So you're left with a m over br 2 capital V. So now you square back everything. So q over m equals to, I made a mistake somewhere. Oh, there's no more. Yeah, it's just 1. No wonder it looks weird. Okay, so sorry about that. So when you square, here become a, then bottom left with a b square r square. You see, for this question, right, I straight away recall this to my mind. Okay, yeah. So formula like this, right? If you cannot recall, then I think it's going to be very hard already. You will be all over the place because you are trying to. Are you going to derive on the spot? You can, okay. But people who can't recall, right? Probably they haven't derived it before. Because if you have derived it before, you will have remembered the formula. So some of these things, right? By now you should start to really make it at the fingertip. Cannot be from scratch and like it will just be too inefficient. Next question, right? This one shows two different curves. So what gives rise to one and the other? So when you see this, right, the key thing is the lambda minimum is different. Therefore, right, it must correspond to different accelerating voltage. The answer is A. And you look at some of the questions, some of the other options, right? It mentions about the temperature. So what has the temperature of the cathode got to do with the setup? Okay, so you see the electrons, right, we strike the X-ray, we strike the metal target and produce X-ray eventually, right, are accelerated by the potential difference, but they are produced at the cathode. The cathode produce the electron. The accelerating voltage give the electron the Ke to ram the target metal with. So the cathode, right, you need to make it hot enough so that you will give out the electron. Hot enough to even hotter, right? Is there any difference? Answer is right, not much. So it is right. If you make it even hotter, the electrons may get liberated from the cathode with a bit more energy compared to hotter, a bit more energy with the hot enough. But the accelerating voltage, right, is what gives it the main bulk. So it's more like, right, you left the cathode with 1 EV, I left the cathode with 2 EV, but eventually will gain 10,000 EV by the accelerating voltage. So what's the difference? No difference at all. This question 30, right? I have a different conclusion from the answer. Okay, here, right, we see that there are various conditions when you put no absorber versus different absorbers, right? What is the count that you get? So by the way, if you can't see the setup, right, of the source is like this, and the detector is probably like here, then you put a material here. So this is your absorber. When you don't put absorber, 1043, put paper 1040. Is that alpha? Because, right, background is already 5. Okay. And you may think background 5, then just 1038 versus 1035. Background, right, is an average. Background is not constant one. Okay. Because, right, background radiation is also a random process. So it means, right, maybe you get 4, 4, 4, 5, 5, 6. 4, 5, 6. So all these fluctuations, right, takes place about the 5. So when you see 1043, right, you should think about it as 1043, maybe plus minus around 5 in the ballpark figure. Okay, yeah, because, right, if this background is 5 plus minus 5, right, could you expect sometimes, right, in a one plus minus 5, maybe plus minus 3, okay, reasonable. Sometimes you just don't have background. So you see, this is within the uncertainty. So you can't tell that there's alpha. Now you put aluminium, then you drop by almost half. So is there beta? Confirm have one now. There's no alpha, but there's beta. Then you change aluminium, then you have nothing. So is there gamma? There probably is. Okay. So my answer is actually C. There's beta and there's gamma. Lead, right? Then almost very little things pass through. Still a few, okay, but this is almost like a background as well, okay. The answer, right, that was given in the solution, official school answer, is right. There's no, and I look up the internet, right, and I sort of agree with the school answer on hindsight. Why there? Because, right, the nuclear website, right, it says that 1 cm of lead can block only around 50% of gamma. I didn't know this. I always remember, right, as long as you use lead, you can block already, because I never do the experiment before. Reading that, right, if there is gamma, what we should expect, right, will be 200 plus, because 1 cm can only block some part of gamma. So this is my initial answer, which is wrong. No big deal, but I feel this kind of thing shouldn't test. Okay, you should just put it as 2 cm or lead, make it unambiguous. Just who knows? Who knows? It must be 1 cm can only block 50%. Why can't? Just by right? If there's alpha, you put paper, you will have blocked all the alpha already. So if you have blocked all the alpha, right, you should see it drop from a 1043 to a substantial. You will see a substantial drop. That's exactly the point. Okay, this is yet another question, right? I feel important for you to know. It's not difficult but important. Okay, what's the concept behind this? The concept behind this, right, is actually something very humble. which is, so let's consider, right, a body has two forces acting on it. We have a F1 and a F2, and this body, right, moved by a distance, okay, and this is called S. So you can say, right, the work done by 1 is equals to F1S. Work done by 2 is equals to minus F2S. Agree? Correspondingly, right, you can write out the power. Rate of work done by 1 is equals to F1V, assuming, right, that this is constant speed. We just want to complicate things here, okay? Then here, right, is minus. So what is the idea number 1? Idea number 2, right, is net work is equals to change in KE. We talk about this many times, right? Almost every time I have a chance, I'll say this because this is fundamental as Newton's law. If you consider what will be the net power? Net power, right, will hence be rate of change of. So now you ask back to this very simple case, right? How do you understand net power? Net power is just add together, lah. Right not? So it's a P1 plus P2. This is net power, right? And what's on the right-hand side is equals to F1 plus minus F2. So it's F1 minus F2. This is actually, so net power is actually, right, F net times V. Therefore, right, F net times V is rate of change of. I'm just showing you step by step how all these formula relate to each other. But put in words, right? What is it trying to say? Net force, right, times the speed is the rate of change of KE. And is it true? Consider lah. You see, net force, right, changes the causes acceleration, right? Causes KE to change. So that's how they relate to each other. Now look at the question, right? You have a mass this amount, acceleration this amount. So up to this stage, right, you already know this is the net force. And to find rate of change of KE, therefore, right, what do you need to do? Just take this net force times the velocity. Do we need to do anything to the resistive force? Okay, this is a redundant info. Because, right, why do we need to know what is the F2 when we already know what is the F net? The only reason why you need to use the F2, right, is if you need to find what is the F1. You know the F net, and all you are interested in is rate of increase of KE, right? There's no need to use F2 at all. So answer is B. So you take this one or multiply by 5.0. Next one, most people got it right. Congratulations. So I just like to show you how this graph, right, and other things are related. So let's look from the light damping graph. Normally we see the X against T, right? Okay, we see the graph is like this, or you always draw in the decay envelope. Okay, how does it translate into your velocity? Velocity, right, will simply be I just draw on the same graph. Okay, so this one will be the V. Okay, why like that? Because displacement of velocity just 90 degrees from each other. Okay, maybe I have drawn it wrongly. Maybe it should be negative sign. I don't care lah. Okay, so when you square the velocity and you get the KE, right? So how will the KE look like? The KE, right, will look like this, and the PE will look like this. And the dotted line that we have drawn in the first place, this is your total energy. So in this question, right, we are asked total energy. So that's this graph. But if we are to be asked KE or PE, right, then you need to know how to get them. Little change for light damping. In your syllabus, you can just take it as no change. Okay, next question here, right? Let's draw a diagram to illustrate, right, what the whole setup is like. You have two panels up in the sky, okay? How far apart? 25 meters. So, right, here your telescope is like this, okay? How do I draw a telescope? Yeah, so the aperture of the telescope is your single slit. So you look, what is your theta at the source, theta of the sources. So it's this angle here. So this angle is theta. And how do you get that? This distance is 335. Okay, therefore, theta source is, need to tangent inverse or not? No need lah. Or small angle. So just divide 3,500 or 1,000. Okay, and whether can be resolved or not, right? You need to go one step further. You are trying to ask, right, compared to Rayleigh criterion, is theta source larger or smaller? So Rayleigh criterion is lambda upon A. Your lambda is 500 nanometer, so 5 times 10 to the power of minus 7. Your A is 200 mm. Okay, so 0.2. Okay, so you can see that the source is greater than Rayleigh criterion can be resolved. Oh, sorry, it's yeah, the number is B. You calculate 25 divided by, you need to press calculator now. No need lah. Really no need. Why? Because, right, 25 divided by 35, right, is like what? It's like 3/4, right? No, it's like 2/4 divided by 3/2. 2/5 divided by 3/3 is around 2/4 divided by 3/2, which is 3/4. Okay, so these are some of the math tricks, right, that you avoid. Why you all cannot finish the paper on time? Because, right, you over calculate. Yeah, there's such thing as over calculate. You may argue, right, I still need to find Rayleigh criterion. Fair enough. Okay. Oh, this one, right, Rayleigh criterion, you see, you have 5 times 10 to the power minus 7 divided by 0.2, right? Divided by 0.2 means times 5 lah. Get this one as 2.5 times 10 to the power of minus 6. Yeah, and here, right, 2/5 divided by 3, this one you'll get 7.5 times 10 to the power of minus 5. Mental sum can one lah. Okay, yeah. Of course, right, mental sum won't work for you if you never practice normal days. Next question is also quite fun. This question, right, you need to think it's different order in your hard copy, right? This question you need to first, right, understand what is the mechanism of EMI. Okay, then, right, go on and ask, based on that mechanism, how will the motion affect the EMF induced? Let me first ask you, right, what is the mechanism of EMI here? What is the concept you use to explain why there is a EMF induced? Faraday's law, okay. Which version? Faraday's law got which version? Have what? Faraday's law got 2 parts to write. Faraday's law states that the induced EMF is proportional to rate of change of flux linkage, rate of cutting of magnetic flux. Okay, so if you want to use Faraday's law to explain, then you use which version? Rate of cutting. Because flux linkage applies for things that have area. Yeah, or so it may be the area changing while the B field don't change. So while area change, right, you have more flux lines captured in the area, or area stay the same, but the B field changing. So also have more flux lines or less flux lines. Okay, so must use rate of cutting. Another way, right, is to use the motional EMF to discuss. Okay, motional EMF, right, is the one whereby you see this wire moving to the right, and then you consider what's the effect on this electron. Then later on, right, you see that when the electrons, right, get let me do a quick check. What is the electrons, right, will get congregated at the bottom side. So at this moment, Fe equals to Fb, okay, and you end up with the formula, right? Induced EMF equals to BLV, okay, but this is B perpendicular LV or BLV perpendicular. We call this motional EMF, right? Don't require anything about cutting of magnetic field or whatever. Okay, it's just going fundamentally, see what's happening to the charges. So using this formula, right, we can judge the EMF in the rod. So this first part, right, EMF of course is 0 because there's no B perpendicular, or they are just parallel to each other. Yeah, portion here, right, this guy is moving this way. This is the V. So V perpendicular, right, is this component here. And you can see, right, this V is increasing at a constant rate because you have a constant acceleration down the slope. Therefore, right, B perpendicular increasing at constant rate, and therefore EMF also increase at constant rate. So if you construct from scratch, right, you should expect first part is 0, then constant rate. What about the last part? Once this guy falls off, right, he undergoes projectile motion. For projectile motion, right, you know that the Ux is constant, or Vx is constant. Okay. Therefore, and Vx is the B perpendicular. The last part, right, will be like this. And there's option B. This question, right, a good number of you got it correct. But let me show you a way, right, how to, as a result of poor options being set, right, a way to get the answer really, really fast. Okay, this ratio gives us the U. You fire photons on the metal, gives out electron. Therefore, right, this number cannot be bigger than 1. C is also B lah. This 1 for 1. It's too ideal already. Then look at A. A is ridiculously small. A is also out lah. That's just because the options are set so poorly. So if I have no time, I'll straight away choose B. Otherwise, right, how to solve this? Current, right, is given by photocurrent is given by charge per unit time, right? It's carrying the charge N electrons, okay, divided by time. So if you make NE over time the subject, you'll get, right, I over E. This is like equation 1. Then you look at the light shining. Who is carrying the power for the light? Okay, is N over N photons times of HF. Therefore, N photon over time equals to P over HF, equation 2. Okay, and anyway, we already know the we don't need to use HF, we just use the energy of the photon. And let me show you further, right, that you don't need to calculate. Let me write out this is equals to 2.0 times 10 to the power of minus 6 over E. And this is equals to 3.1 times 10 to the power of minus 3 over, right, 3.11, or rather, right, see, you want to convert this into SI unit. So what do you need to do? You need to times 1.6 times 10 to the power of minus 19. Essentially, right, times E. So when you take equation 1 divided by equation 2, right, can you see the E cancel out? Look at this number, 3.1, 3.1. So equation 2, what's the coefficient? It's a 1. Equation 1 coefficient is 2. Equation 2 coefficient is 1. Answer is 2. No calculator. This question is interesting. Normally we see A against T, right? We know the graph is a exponential decay shape. And now this A naught, one period later, you'll see half A naught. But you see, in this context, right, this is 33 years. We only want to know what is the number of cesium that decay in 2 hours or in 2 days. Therefore, right, you have to zoom into this graph, so you zoom into until you can see 2 days. So if you zoom in enough, right, this graph will turn into this graph. Because, right, you zoom in, zoom in, zoom in. Here is a curve. Zoom in enough, it actually is constant over a period of just 2 days. So you just take, right, this number, the activity. How do you find a number that decay? This is telling you the rate of decay, right? To find a number that decay, the rate times the time. So 86400. 86400 is how much? 864 times 2 is 17, right? 864 times 2 is 17. 17 times 4 is 68. So it's 69. Okay, this question I think is fairly well done. So basically, right, you want to find the speed after 4 seconds, you need to solve for the vertical speed after 4 seconds first. So the strategy, right, is to find Vy, or Uy will remain constant. The Vx, right, is equals to, so then you recombine to find so that's a strategy. So break it down into the Y component. You have, right, taking upwards as positive, 35, try the formula first. So V equals to U plus Vy equals to 35 sine 40 degree plus minus 9.81 times 4. So solve for this Vy. And after that, right, the V will be doing the Pythagoras theorem, okay, to these two. Let me tell you, I look at the answers, right, I get worried. Why? Because, right, out of the 50% who got this question wrong, most of them chose C. And C and D, right, are the two answers I will eliminate without even doing anything. Can you fire something, right, while it's in the air? Is higher than your initial position, right? Yes, GPE, right? So your KE component is lesser than before. So how can your speed be higher than the initial one? C and D, right, are the obvious wrong answer. Dare to tell you, don't choose me. And half of you choose them. They're screaming at you. Don't choose me. I don't make sense at all. I'm ridiculous. Okay, next question. Success rate is not bad. So just quickly show the diagram. I want to just show you, right, the faster way of doing it, okay, in case, right, you're not aware. So here I will have a mg sine, here I have a mg sine 20, and I have a friction. So right, the F equals to MA, mg sine 15 minus F equals to MA. Okay, equation 1, mg sine 20 minus F equals to M, equation 2. Sub together to solve for the F. What's the step? Let me see. Okay, that's it. Missing out the mg. Question 11, the success rate is not bad. It's a bit better than I expected. This is and let's call the neutral point here. This is the X. So you are expecting, right, the G1 and the G2 to be equal. Okay, Gm1 over x squared equals to Gm2 over d minus x whole thing square. Okay, so you flip and square root. Okay, so you have x over square root m1 equals to d minus x over square root m2. Make x the subject and you will get C. Question 12, right? Out of 4 options, which one to eliminate? Without thinking on which one to eliminate, because you're moving something away, right? Just like lifting something up, GPE must increase. Okay, then after that it's easy already. The formula for potential is equals to Gm minus Gm over R, right? So when the radius, when the distance, right, doubled, you expect the potential to half. So at Y, right, it will be minus 4. Okay, so the difference is 4 times 2. So gives you 8. Change in phi equals to -4 minus 8. So it's +4. So the change in U equals to mass times the change in phi. Honestly, right, I feel question 12 is a giveaway. Okay, question 16. I don't know how you go about thinking, okay, but one way, right, the easy way to choose, right, and to interpret this one is to see. This is a F against R, okay? I can think about it as F against X, yeah? So it's distance about fixed point. So this graph must remind you that this motion, is a SHM. So if this is a SHM, right, how would the potential energy of a SHM, okay? So it simply be this parabolic shape law. This is your PE, and the KE will be this one. Is it familiar, right? So this is number one way of thinking, which is the easiest way. Now, I would like to introduce, right, or relate this to another concept so that you can see that there's a link, which is, right, for all situations that involve potential energy, okay, you can relate it to the force in such a way. F equals to minus du over dr. Essentially, right, it's telling you the force, right, is actually the negative potential energy gradient. So if you just use this formula, and let me give you an example. See, Fg is equals to minus, the U here refers to GPE, right? Or Fe also, are they the only ones in your syllabus? No, you even have, right, this formula can also apply for F equals to Kx. So back to here, how do you use this shape of the FR graph? Let's say you didn't occur to you this is SHM and you use this formula instead. You can brute force it out one, okay? Which is right. This is the EP against R. Well, here I have a positive, okay, but this F, right, is like decreasing, okay, decreasing. So we have positive F. So it means, right, I must have a negative gradient because F is the negative of the gradient. So if F is positive, the gradient must be negative. So negative, yeah. And here the F is large. That means gradient is steep because the gradient is the F. And the F become smaller as you go closer to 0. Smaller until here becomes 0. Gradient becomes 0. What happens on the other side? Become negative, but increasing in the number. So here gradient must be positive and increasing in steepness, steeper. Okay, so that's how you can construct using this shape. I mean using this equation. If both are L, create a disturbance to the tube and cause the sound to manifest, right? Okay? So the standing wave that forms, right, will be the fundamental. Okay, and now, right, if you relate the fundamental to the length, you see, right, for here, the lambda 1 is equals to 4L. The lambda 2 equals to 2L. Yeah, so it's twice. This is number one. Number two, right, is you need to realize for the same medium, the wave is the same. So V equals to F lambda. Okay, therefore, F is proportional to 1 over lambda. So why is this the same? Or rather, right, under what condition? Same medium. Okay, the condition for the medium must be the same. Okay, for example, right, air at room temperature versus air at high temperature, different. You have a different string under low tension, so you have wave in a string versus string under high tension, also different speed of the wave. So same medium, same property. With this, right, then you can see how it must be C. Because the wavelength is half, so the frequency is doubled. Question 21 is quite popular. I see in a number of schools question. Okay, let's look at what are the forces acting on here. We cannot use charged particle. This is not correct. Particle usually is like those subatomic particle, and subatomic particle, right, weight compared to the electric force acting on it, right, is very many order of magnitude away. That's why, right, when you fire an electron or ion into a E field, right, you shall never consider the gravitational pull because it is too small. So here, right, more correctly, such a question, right, should be a charged object. Okay, real use case is actually a oil drop. So cannot be a particle. Anyway, come back to here. So this is your Fg. This is your E. Yeah, when at equilibrium, these two are equal. So now, right, when you increase V, what will happen? Okay, E will move to the upper plate. Is to tell you, right, that this is the upper plate is negative lah. Okay, so let's just this statement, say or don't say, also never mind one. doesn't matter. So let's consider, right, what happens when we actually change V in either direction. So let's consider when V increase, okay? So V increase, right, what will happen? So this will mean, right, that the net force will be, I better don't put up arrow. So this particle, right, will move up. Consider, right, when this particle move up, is moving in the direction of Fe and moving in the opposite direction of Fg. So what will happen to the GPE and EPE? To answer this, right, let me help you recall one concept, which is, right, done by, for example, Fg is equals to minus change in GPE. In the same way, right, work done by Fe equals to minus change in EPE. In general, work done by whatever the force equals to negative change in the PE. So this is the concept. So what is this concept saying? If I allow the force to move things, right, in the direction that it wants, its potential will drop. Potential energy will drop. Potential energy is what? It's something you store in a bank. So if you allow the force, right, to do work, you have to take things out from your bank. So what happened to a bank? The bank will have a negative change. So the amount of work that you do, right, is not free one. It comes from your bank. Whereas, right, if you curb yourself and you allow the force to negative work, that means, right, energy is being stopped back into the bank. For example, if I let you do whatever you want, then your potential A grade or chance will drop. If you curb your tendency, your desire, or you do opposite, then your potential to get A goes higher. So this means, right, if this one move up, so it move in direction of Fe, right? GPE will decrease, EPE will, okay? So that is what we get from vice versa, right? When V decreases, so F net will be down, so you will have particle move down, and therefore you have a GPE, EPE. So you choose a statement that is consistent with our conclusion, which is B. Back to the formula on the left-hand side, in case you find this very difficult to understand, too mathematical, let me give you a simple way to see it. Take gravitational field, right, or as the concrete example. Weight is always acting down, right? When you move the object up, what happened to the GPE? GPE increase, right? So change in GPE is a positive term. But what is the work done by the gravitational force? Gravitational force is always acting down. The displacement is up. So work done by gravitational force is opposite. Gravitational force is acting down, but you move the object up. Work force times distance moving direction. So you see, compensate, right? Then you need to have a minus sign there, because one will be positive, one will be. Don't you feel the topic that you seem to know the least about, right, is actually energy? Right now, along the way, right, you realize, these things, how come I never know one? Because when we do WEP, right, everyone just brush across, right, and think that it's easy. So I always do also. When I teach WEP last time, I also bring it across quickly. I assume people know. After many years, then I realized, right, that is for the C. Back to here, this kind of question about the minimum, it arises when one electron loses all its energy and produce one X-ray. So you will have the EV accelerating equals to HC over lambda mean. Okay, so lambda mean proportional to 1 over V. So you want to have the lambda mean for 6 versus 8 over 6, 1.3. Okay, now this one, right, why so many people get all sorts of answer? 40% got it wrong. So basically, this is just the uncertainty principle. Okay, delta X, delta Px or greater than H. Note, this one need to be careful. Whenever you apply uncertainty principle, right, this and this must be same direction. Let me give an example. What does it mean? Let's take this as a Y direction and X direction, right? So when a particle goes through this slit, right, is there a momentum, uncertainty in the momentum? Okay, so this uncertainty in the momentum in the X direction, maybe. But for this case, right, that is not what we want to relate. Slit, because, right, in this case, the slit, right, is offering a uncertainty, right, in the Y direction in terms of displacement. This and this, right, don't match. So this one is to match with what? It's a uncertainty in the Y direction. Here I'm just putting X and X in the equation above, right? Inequality above in general. Okay. For this question, there's no issue because there's no other information that will trouble us. But what I draw here, right, is a TYS question on this. They actually test you which of the following, right, corresponding uncertainty that you can use the uncertainty principle upon. Make sure that the direction is the same. Okay, so with that, right, just solve. People choose B, a number of people choose B. People ask for uncertainty momentum, never ask you for momentum. People who choose B, right, you take the mass times the velocity. That's the momentum, not the uncertainty. What? EJ question, I sent it in the before, okay, yeah. So what will happen? This problem, right, we need to deconstruct it into simpler part, and we consider a series of collision. So first up, right, is you consider when A collide with B, okay? So, but before we do that, right, let's have some building block. When two masses collide, right, M1 and M2, okay, where M1 not equals to M2, okay, there wouldn't be any simple pattern in the collision. There wouldn't be, let's say, right, this one, the U2 is 0, and you have a U1. So, right, after the collision, both will be non-zero one. So it may be like this, it may be like this, not be like this lah. Okay, but both, right, will be non-zero. This M, and this is an elastic collision, right? And this 0. After the collision, this guy will take the host velocity. This guy will be 0. So essentially, right, what they will do is they will swap for elastic only. So these are actually the two things that we need to know. A moving one collide with a stationary one, and the mass are not equal. After the collision, both will be moving. Can you verify? Can. You refer to the message I sent on WhatsApp, right? Go and take a look at the exact working. With that, right, A and B, after the collision, right, what will happen? Before is 10, before is 0. After will be some velocity. After this will be some velocity. And this one I want to use it. Let me just call it B. I don't know, I don't care. Then after that, right, I want to find what happened to B and C. B and C, right, B ended off with this velocity. So this will be its initial velocity. And we put it here, and C will be 0. After the collision, they will swap. So this will become V, this will become 0. And you can say the same, right, for C and D, or D and E. Eventually, right, when it comes to the last one, which is E, so this one will come in with V, E will be 0. After collision, D will be 0, E will be moving. E will be moving.
Why is 0?
Sorry?
Why is 0?
Because all of them are initially at rest. What? The top line is always the initial, bottom is the final, right? B is moving, knocking into C. So after the collision between B and C, C move. After collision between C and D, D move. After collision between D and E, E move. So what's the net effect of here? The momentum that B gains, right, after A knocks it off, transfer all the way to E. You give you, it's like play a relay like that, okay, all the way to E. Now you need to consider, what about E and F? E and F, right, this one is non-zero. This is the V. Therefore, right, after that, so I'm just drawing a two-sided arrow. It could be one or it could be the other block. So F will move, E will also still move. Because, right, it is not the same mass scenario whereby they can swap. So if they cannot swap, right, that means E must have some momentum one. What direction, I don't care, because here they only ask move or don't move one. So after the collision, E will be moving. After the collision, B will be at rest, A will be moving. Is this difficult? Okay, quite difficult. I didn't get it at the beginning. I need to go and think, discuss with my friends, unfortunately. This one I will post and send. I forgot to include this one, but I will skip this first. I didn't go through this with the other class also. Okay, what's the frequency at which the coin lose contact? So this is the kind of scenario, right, whereby you have a platform that's undergoing SHM, this is a top and bottom, and you place an object on top of it. Here, right, you have a normal contact force, and you have a mg. Okay, so it's a mg minus normal contact force equals to ma. Okay, and this a, right, is the acceleration of the body, which is in this case performing SHM. So this is the normal case. So you see, if, right, thing is oscillating very fast, okay, let's say up and down very fast. If omega is very large, right, what happened? Then your means, right, because you see, A equals to omega square x. Let's say you increase omega while you keep x constant, then you'll increase the acceleration overall. It means that the normal contact force will become smaller. Alternatively, right, if you increase x while you keep omega constant, it will increase, normal contact force will also become smaller. So to lose contact, right, means this whole thing, the acceleration, right, is too fast until, right, n becomes 0. In other words, right, we are considering the extreme case whereby the A naught okay, which is equals to omega square x naught, right, greater than g. Once this one greater than g, then the oscillating platform will accelerate faster than the ball can drop, and therefore you lose contact. So this is what we are solving against. So you have 2 pi f whole thing square times x naught greater than g. So your x naught here, right, it's not 14 but 7 cm only, okay, because 14 is between top and bottom. That's the thing to be careful about. Answer is C. 22 is reasonably well done. Okay, see that this thing is swinging enter versus exit. Okay, so the in and out must produce EMF of different pole. Okay, so that's the number one thing. Therefore, right, that distinguish between AB versus CD. So one side must be plus, one side must be minus, whatever it is, because one side is enter, one side is exit. You must have a opposite kind of EMF. That is a opposite change in the flux linkage. One is an increasing flux linkage, one is a decreasing flux linkage. Number two is to distinguish between A is constant, B is decreasing. Why decreasing? Because of damping. Why it got damping? Called Lenz's law. And moreover, closed loop current can flow. Got it? If current cannot flow in the across AB, right, then you see how you know current can flow? Because it's closed circuit, right? There's a resistor connected. Yeah. So it means, right, this resistor will heat up. Energy will be lost in the circuit. As the energy will be gained in the circuit, lost by the oscillator, hence damping. Next one is tough. This one, right, I think people will get tripped by the question. Okay, so let's look at the original scenario. Original scenario, zero acceleration because moving at constant speed, right? Let's look at the forces. So you have mg, okay, and this spring is being compressed there. Because it becomes 7.5 cm. At first it's 10 cm. So the spring force, right, and this is equals to K times 0.025, which is the compression. Then later on, right, when this leaf is moving at a moving up, constant deceleration. So let's put the moving up, right? Decelerate means what? A must be downwards. So now, right, when the forces, mg is still the same. How must the compressional, the spring force be, right? That force is downwards. It must have been still upwards, right? But smaller compared to before. Okay. So let's call this kx, and you can solve already. Here you will have mg minus kx equals to A. Okay, problem is, right, we don't know what is the M. Could we find out? Look at the original situation, right? You have mg equals to 0.025. So M is simply 0.025 K divided by G. So we are making use of the fact that at first, right, they are in equilibrium. You can sub in. So here you have, right, 0.025 K minus AX equals to 0.025 K over G times all the K. So X equals to 2, or rather 0.02. Some people will ask, okay, or rather yesterday someone asked me, why can't the spring be stretched? Why should it be compressed? There is a chance. There's a chance the spring could be stretched. Okay, you see, this spring can work both ways. It can be pressed down or it could have been put longer. So how do you know, right, what is the case? You simply, right, look at the acceleration. You see, here, right, the acceleration is equals to 2. Or rather, right, let's consider more generally, right, if the spring is being stretched, right, okay, what does it mean? It means the spring force is pulling it down. That means the spring is being stretched, spring force is pulling it down. So the tension is this way. What can you say about the acceleration? Now you have mg and tension both pulling down. What can you say about acceleration? Greater than g, exactly. So if here shows you -10, -20, sorry, not negative, 20, okay, then you can tell that the spring must have been stretched rather than being compressed. But since this one is less than g, therefore, it must have been the compressed case. And I find this is yet another important question, okay, because, right, it's fundamental. This one, I don't know why so many people wrong. The formula to connect V R omega is V equals to R omega. Yeah. Now, read the question. Common angular velocity, constant velocity. So this one is a constant. What happened to the R? Decreasing at a constant rate. This R against T, constant rate. Constant rate times a constant. This one changed to V. Okay, question 10, you're forgiven for not being able to do this. Just teach you the trick, okay? This one won't come out for exam 1. Springs in parallel. What is the formula to get the new spring constant? It's actually right, similar to the resistors. Did I say it wrongly? No. Springs in series. Whereas right, springs in parallel, right, you'll get K effective equals to K1 plus K2 and so on. Yeah. So let's figure out, right, this one. So this portion here, since they are in parallel, right, so you just sum up their spring constant. But what does it mean? See, when two springs are in parallel, right, it makes it stiffer. I'm not sure whether when you are young, you sleep before in those kind of, what I call that? Got the spring, you hang the thing from the ceiling, then the baby sleep inside, and you oscillate the baby. Yeah. So if it's a fat baby, right, you need to have two springs. Otherwise, the baby, the amplitude become very large. Okay. Spring in series, right? The K add up. K is a representation of stiffness of spring. Okay. So here become 2K. And now, right, now this one is series. So you use the parallel resistor formula. It's opposite. Yeah, so it's a 1/1 plus 1/2, then flip around. So you get 2/3. This question, right, this bubble go from the bottom to the top, right? Okay, what happened to the volume? So let's consider, right, the formula PV equals to nRT. Okay, you have a constant temperature and same amount of gas inside, right? So same N. So this turns into, right, the V proportional to 1/P, right? Because you are studying the volume. Then question tell you outside is already called a PATM. Yeah. So here, right, purely PATM. At the bottom, right, you will have PATM plus H rho G. And this H rho G, right, is just 2 times of PATM. So total is 3. So if the pressure become 1/3, the volume will become this question, how to see the direction of the E field is always perpendicular to the equipotential lines. So the E field is which direction? It's high potential to low potential. So this E, right? But what will be the force on the charged particle? We don't know the charge. Okay. So it could have been, right, like that or like that. Yeah. So we don't know. Therefore, right, the deflection could be up, could be down. So, but that's not the point. It's to distinguish between 1,3 versus 2,4. So what's the difference? You see, 1,3, right, the moment you enter this region of E field, it starts to bend already. It makes sense because once there's a force, there will be a change in the direction of the path. 2,4, right? This guy is very steady. He can move straight for quite a while. So obviously 2,4 is wrong. And where's the field strength high? E is equals to minus dV over dr. So you look at the closeness of the equipotential line to tell you how to see equipotential line, how to visualize it. In geography, you learn the contour line, right? Let's say this is a mountain, going hiking. Going this way is easy, right? Because you know it's gentle. Going this way is very steep. The steepness, the closeness of the equipotential line is the steepness of the slope, okay? And the effect of the force. So what? 1,3 and answer is P. So it's A. Okay, next one. Here we are using the formula for P proportion P because nRT. The N and the V are constant, right? So this reduces to P proportional to T. Let's look at the numbers, okay? The relationship is very easy. 25 degrees Celsius, right? Don't see as 25. Always, right, once this number appear, it actually means it's 300 Kelvin. You may think that my math got problem. 273 plus 25, why is it 300? Yes, because it's 298 is 300, okay? Always give you what? 25 degrees C and 125 degrees C is to mean 300 and 400 Kelvin. And when you have this and the reading is at first, right, 200. So this reading is actually, right, the actual pressure is 300 because it's excess pressure over PATM. So the actual one is 300. Now you see, after driving on the hot road, right, the air temperature become 50. So this is 325 Kelvin. So what is the new pressure? Okay, new pressure, right, will hence be proportional. I see the number already set very nicely. 300 Kelvin, 300 the 300 kilopascal. So here 325 Kelvin, here also 325 kilopascal. But the reading on the gauge, right, to minus 100. So reading is 225 kilopascal. So 200 versus 225, okay, the change is 25. 25 over 200, 0.5%. Okay, this one is poorly done. the spread, right, is 25% for all options, purely by luck one. When you see this kind of spread, right, the 25% that got it right, I will believe that they also guess one. That's all other people, you see, it's all equal, okay? Recall, right, for SHMV against X graph, okay, it seems that this is reflecting velocity and X, but there is actually a hidden dimension of, do you remember this? P is here. A while later, where will P be? So what will happen to the displacement for P? It will go from wherever it is further from equilibrium position, further, okay? So with that, right, can you judge? Cannot. Because, right, this is a F against T graph. So you see F against T, don't panic, because you see F equal MA, and A proportional to minus X. SHM relationship. The X against T graph, right, will be, you see, A, B, C, D. So which particle should you choose? Number one, you want the particle which is at the negative X region. Number two, you want the particle who is at the negative X region and going more negative then. So who is going more negative? A while later, where is D? D will be there. Oh, you see anti-clockwise? Got already. Did I get the conclusion wrong? Let's work it out. Let's work it out. I teach you how to work it out. Let's draw a simple spring force. I draw a left to right. Yeah, I better draw left to right. This is easier since our X is the, I say that this is equilibrium position. Okay, there is 4 stages of this motion. It could have been on this side. So I'm drawing the V. Okay, it could be on this side and going right. And let's put a convention. So let's put this as positive. Okay, and let's label them. This is stage A, this B, this C, this D, and match them to parts of this the ellipse. So when it's at A, right, you are at positive X and moving in the positive direction. So this must be, then A finish, you reach the extreme position, you come back, so you'll be B. So you are still in the positive X, but moving left. So your velocity will be negative. So this is B. So you will have been A first and B. So you pass the equilibrium, you go to the negative region, and you are moving in a negative direction. That's C, and finally D. So that gives us a clockwise, always clockwise one. This one is embedded in the mathematics. Okay, what's the magnitude of the maximum force? This one is easy. F naught equals to MA naught equals to MX naught omega square. Okay, so question is, right, what is the omega? The formula is always, right, X naught sine omega T, right? This is your omega 3 pi. I think, right, I didn't check the answer. I didn't know what the other numbers mean, but I'm just suspecting, right, that you don't know what is the omega. So the answer is A, if you have gotten it right. Sometimes, right, when too many people get it wrong, right, I doubt myself because I never calculate, or rather I use mental sum, right? So I'm not sure if I made a mistake or asked too many people wrong. This one, my answer may be wrong. This one, my answer may be wrong because I remember I calculated this wrongly. So the answer is A, if I'm not wrong. Let's just work it out. So what's going on here, right, is this, okay? You have, let me draw it on the side, okay, because this diagram too messy already. This is the screen, okay, and this is the original white light. So this is your 0th order. So let's take, right, pink as this 700. Okay, and violet as this. So I will have, right, first order of the violet here, first order of the violet here is 1 and this 1. Okay, I have first order of the red here, first order of red here. This portion here, right, is your first order. First order, you'll see the full rainbow. No complication. Okay, second order, right, you take this one further. So this is the second order for the violet, and this is the second order for the red. But, right, the third order for the violet is here already, and the third order for the red is further away. This is the part, right? So let's label it properly. Second order to second order, you see this is second order. Third order is here. Okay, so where's the overlap? Is this segment here? I need to take 2 angles minus each other. What is causing the overlap? It is, right, the second order of the red overshoot into the third order of the violet. Okay, so who is bigger? Bigger of red 2, okay, larger, and smaller one is the violet of 3. Go ahead. So it's equals to sine inverse. This is what? No. 2 times of 7 times 10 to the power of minus 7 over D minus sine inverse 3 times of the 4 times 10 to the power of minus 7. Anyone have performed this calculation? If I don't remember wrongly, someone told me yesterday that the answer is A. Sine inverse 2 times, then minus the angle. Hey, the difficult part is not how to calculate that. The difficult part is how to form this. Form this really, you should be very happy. Just, how to calculate the D? D from here, you see, 300 line per mm, right, means 1 mm divided by 300 lines, okay? 0.001 meter divided by 300 lines. 3.3 times 10 to the power of minus, is it minus 6 or minus 5? Minus 6. A, okay. Okay. The next question, right, we have a compass needle, okay? And in this region of space, right, there's a magnetic field due to Earth, which is like this, right? This B due to Earth. Now, right, you put a wire, which is somewhere here, okay? And current pointing down. So let's take this as a top view, okay? So you're looking from the top. So the current is flowing this way. So what's the B field around the current? You use your right hand grip rule. It's all these concentric circles, right? So at the location of the magnet, okay, of the compass, sorry. So the B field is like this, right? Not? So it's to the right. And we can put these two B field together. So this B due to Earth, this is B due to the, okay, due to current. The resultant deflection, right, will reflect the resultant B. And this angle, right, that it flipped by will be the inverse tangent of B due to the current, B due to Earth. So this is the strategy. And now, right, you still not done yet because, right, you also don't know what is the B due to the current. That, right, you need to employ this formula. B due to the current, right, this is equals to mu naught I over 2 pi R. This one, all this must memorize. For the flat coil, for the single straight wire, and for the solenoid. Flat coil is mu naught N mu naught I over 2R. Then the solenoid mu naught per unit length. Got it? So if you've done it correctly, I think 52 degrees east of north. No, why they say this, right, is because, right, it came from north, then you're going to the east. That's why I say east of north. You can also mean it, think about, yes, northeast side. This formula, yeah, we're almost near the end. Is this the last one? Oh, yes, the most tiring lesson ever. Yeah, okay. So here, right, you have, it looks very long, right? And like the previous magnetic field question, right, if you don't know the particular concept, right, just now it was the curvature in a B field. For here, right, this is the velocity selector formula. This V goes to E over B. If you don't know this, right, then you will take even more time. Starting point is you already know this. You can see, right, that this E is what? 6 times 10 to the power of 2. Bottom is 2 times 10 to the power of 5. So you get, right, 3 times 10 to the power of 7. Okay, so this is the V as it enters this B field. This guy will go in a semicircle and hit. So this 60 cm, right, is equals to 2R. That means R is 30 cm. Then finally, right, you use the formula R equals to mv over bq. So this is 0.3. You already know this one. Want to find. So m equals to rbq over v. So this is 3. This is 1.2. This is 3.2 doubly charged, on this 3. And this is 3 as well. Okay, so what is 1.2 times 3.2? It's around 3.8, 3.9. Calculator. So far, this whole paper, right, only one question, which is the sine inverse, the angle, cannot calculate. And also the tangent inverse. Okay, I have no method. You understand what I'm doing, right? Here,